Welcome to this initial video within a series for the Patina project in the Open Device Partnership organization. In this introductory series, we are going to cover a range of topics, from how the project is organized and motivation for doing the work, to a developer getting started an orientation guide, and more advanced topics like how to do source debug using the capabilities built into the Patina project. This is the first video, so we're going to begin with the most basic material covering how the project is organized and how it compares to other UEFI projects out there. We begin by looking at what exactly is the Patina project. Patina is a UEFI compliant pure Rust implementation with what we call a component-based architecture for writing monolithically compiled firmware using dependency injection. That's a lot of ways to describe the work that we're doing, but it most succinctly describes how it is organized and what we're trying to achieve. We began this work with a primary motivator of memory safety for not only switching to Rust, but a memory safe language in general. And the reason for this is that it eliminates entire classes of memory vulnerabilities. Here, using Rust ownership model, borrow checker, and other features and tooling of the language. As we began this work, compatibility was a major concern. Today's platforms typically have hundreds of C drivers, even just in the Dixie phase alone, and we need to provide a way to be able to continue dispatching those drivers with no disruption to platforms, or at least as minimal disruption as possible. Patina does that by allowing us to dispatch PI-based C drivers alongside those monolithically compiled pure Rust components mentioned earlier. This gives us a strategy to continue supporting existing platforms, but increase the number of Rust drivers over time. Reliability is also very important. Rust gives us compile time guarantees we don't have in other languages. It's also traditionally been difficult to write unit tests for firmware code, especially in C. We have placed an emphasis on this in Rust from the beginning. We have over 80% unit test coverage and comprehensive static analysis using other tools as well. Everything we do is open source, Apache 2.0 licensed in the Open Device Partnership on GitHub. For more details, you can read the document linked below in our MD book. A natural place to begin when looking at UEFI support in Rust is the STD UEFI target, and then the various crates out there for UEFI. In this case, one of those is, of course, Patina, and in this section, we're going to compare what Patina offers versus that STD target. Beginning with Patina on the left, it is a pure Rust Dixie core that replaces an entire C-based Dixie core and therefore dispatcher. It has monolithic compilation, as mentioned before. This is in contrast to how C firmware is typically compiled, where the core itself is an EFI binary, and all of the drivers that it dispatches are also EFI binaries. In Patina, we compile those into a single EFI image. That allows us to best make use of Rust's compilation safety model, including the borrow checker and so on. Patina also has that custom component model with dependency injection. This dependency injection is largely a replacement for dependency expressions and platform initialization based firmware. Patina takes an opinionated security stance as a project. This is important because not only are we trying to modernize the language, but we're trying to modernize firmware itself and cutting some features from places that have led to problems in the past. This means that Patina is not fully PI spec compliant, and that's by design, but it is fully UEFI spec compliant. If you're not familiar with these specifications, the platform initialization specification largely covers how firmware is written and interacts with other firmware. And the UEFI specification focuses on ABIs, calling conventions, key services that are used between external interfaces and the operating system and firmware itself. Patina has deep platform integration. It controls the memory map. It implements the UEFI boot services. It controls dispatch, and in fact, has two dispatchers that cooperate with each other. One is that PI dispatcher that's providing us backward compatibility support to be able to launch today's Dixie drivers written in C, and the other one is the component dispatcher, allowing components in pure Rust to be dispatched that are using the dependency injection model. Looking at STD, that is a way to be able to use the Rust standard interfaces to write UEFI code. It allows individual UEFI applications to be written, and those will likely be separate .EFI binaries because they are going to be loaded from various sources like a flash drive or maybe a network share or placed on the EFI system partition. However, they are given to the system, they are going to be separate .EFI binaries individually distributed. The main advantage here is that you can use standard Rust patterns to write your code for UEFI, and it will link up to the underlying services implemented by a core. This means it can run on top of any UEFI implementation, Patina or EDK2, and you can swap out Patina or EDK2 from the underlying firmware for a device, and these applications will continue to work because they have that abstraction through the Rust STD interfaces to the boot services down to the underlying core itself. This is a good approach for UEFI shell tools, test applications, and utilities where you just want to work with the familiar standard library and you don't want to have a bunch of extra crates and infrastructure on top, and you need compatibility in those tools and applications across a diverse set of platforms. Patina is not the only UEFI crate out there. In this section, we're going to compare Patina to some other common Rust crates, namely UEFI-RS and REFI. We're going to look at different aspects of these to better understand how they differ from each other. Beginning with primary scope in Patina. Patina is unique in the sense that it provides a complete core environment from the ground up in pure Rust. This means that it does not rely on any underlying C code because it starts at the most basic needs of firmware, implements those in Rust, and continues to do that up the stack. UEFI-RS is a wrapper library most useful for UEFI applications and drivers that want to use an idiomatic Rust interface to common services needed to write that code. With UEFI-RS, you are largely writing separate EFI binaries in the traditional sense. So this might be UEFI applications or individual Dixie drivers, and you're able to do it using those Rust interfaces that abstract themselves from the underlying core. So for example, a UEFI application written using UEFI-RS can run with an underlying pure Rust Patina-based Dixie core or a Tiano Core C Dixie core. REFI provides raw FFI type bindings. These stick very closely to the UEFI specification, and there's not a lot of implementation around those types intentionally. This keeps it simple and clean and allows it to be a building block that is used across a lot of other places. For example, both Patina, UEFI-RS, and other projects use REFI as an underlying building block for how they construct their code on top. Looking at architecture, Patina is again focused on providing that full core environment with a forward-looking monolithic model using components and dependency injection, but also providing backward compatibility in the meantime. Patina also provides an SDK. So while the core environment and the benefits that come with that is its primary purpose, the SDK is general purpose and it can be used by code that is not using the Patina core itself. So that's another option in terms of a crate from the Patina project that can be used even if the core is not being used. UEFI-RS is focused on those standalone UEFI apps and drivers. This is where you might write a UEFI application in Rust, or maybe a few one-off Dixie drivers in Rust. And you want them to have a nice clean Rust interface and be abstracted from the underlying core. So they could work with a Patina Rust-based Dixie core underneath or a C-based Tiano core Dixie core. REFI, again, is largely focused on those low-level type definitions. So there's not much there architecturally other than trying to keep things simple and as broadly applicable as possible. When we look at the driver model, Patina implements a full driver model using that pure Rust-based system with dependency injection, and you'll learn more about that in later videos. UEFI-RS continues to rely upon UEFI interfaces using protocols, and because our EFI is a lot of those basic type bindings, this is not directly applicable there. In terms of build output, Patina as a overall project focuses largely on a single EFI binary that includes the core coupled with platform selected functionality in the form of those components. It can support, of course, dispatch of separate EFI binaries as well, but that's its primary model going forward. UEFI RS is used for individual EFI binaries. So this is a way that you would produce an EFI binary using Rust code in Rust interfaces, and you may be able to use that resulting EFI binary in a variety of places. Looking at target use, Patina is oriented toward platform firmware. It works for UEFI applications. It works as well for tooling. And so there's really at least two large aspects to it. One is the SDK, which provides a lot of PI spec and general firmware functionality using idiomatic Rust interfaces and definitions, in addition to the core itself and being able to have a pure Rust environment built from that. UEFI RS is focused largely towards UEFI applications and tooling and gives you that wrapper library to build those. On this slide, we're going to look at a visual representation of some of the concepts discussed previously. On the left side, we have different types of modules. UEFI applications at the top, followed by Dixie drivers, and then the Dixie core. Over on the far right side are crates and how those are applicable to these different types of modules. Starting at the top left, UEFI applications have some examples there, such as Grub, the Windows Boot Manager, EFI Shell, and other types of UEFI applications, including the ones listed, and you may also be familiar with third-party disk encryption and so on that are in the form of UEFI apps. If we look over at Rust Crate coverage, you have the most options for these types of modules. Our EFI, of course, applies across all of this. You can use those type definitions if you're writing a UEFI application to have those types from the UEFI specification conveniently defined for you. You can use Patina and its SDK in order to write these. You can use UEFI RS with its wrapper library, so you can write your code in Rust and be abstracted from underlying details. You can also, if you're familiar with STD and you want to write your code using that, you can do that as well, and that will abstract you from some of the underlying details like how the allocator is implemented and things like that. If we go down to the next level of Dixie drivers, to some extent, the UEFI RS model applies here as well. But whenever we look at Dixie drivers, we really have two different types, boot services drivers and runtime drivers. Boot services drivers are the most common kind. These are active during boot itself, and they are no longer persistent after what's called exit boot services, which is where we transition the system over to the operating system. Runtime drivers continue to persist into the operating system. This is a much smaller set of functionality in the Dixie phase that continues to live into OS runtime. Patina supports both of these models. However, Patina components cannot be runtime. Because everything is monolithically compiled into a single image, that code image is a boot services image, and so its memory persists for the lifetime of the boot itself up until the OS transition. And Patina still depends upon separate EFI binaries for runtime support. But the Patina core and the SDK dispatch both of these drivers and allow you to work with the Patina interfaces for both. And if we look over at the far left side, this is largely platform developer territory. While at the application level, application developers may not be thinking about individual platforms that their application is going to work with. It may need to work with all platforms, and so they have to use interfaces accordingly. Dixie drivers are the ones that provide the system initialization, the register initialization, and so on, that give us the foundation to be able to write those applications on top of. And this is largely done by developers working on platform firmware for that device. Finally, at the bottom are core developers working on the Dixie core. Again, this is applicable to Patina because Patina provides the Dixie core itself. Core developers are an even smaller set of developers. These are ones that work on a core implementation that is used across all platforms and ultimately all applications. So there's typically a very small set of developers working on this, and it's used in a lot of places. And Patina happens to fall under the core category since we are providing a pure Rust core. Here we're going to look at the difference between a underlying C Dixie core and a Patina Dixie core, regardless of how you have written your applications and drivers on top. If we look at the left side, you can see that there could be applications written in a variety of methods. If you want to write them in Rust using the wrapper libraries provided by UEFI RS, that's one approach. You could have written it using STD as well, in addition to a C authored UEFI application. These are going to go through the boot services table, and that is the primary abstraction that allows these different ways to work with an underlying C Dixie core. Now, whenever you go through this though, although your top level is written in Rust, you're ultimately calling down into a C implementation because the UEFI boot services table is function pointers into that C code. Now, if we look at swapping that Dixie core, this is one of the primary goals of the Patina project, is to be able to write the functionality ground up in Rust, not just the top level. All of that continues to work. Regardless of which approach we chose, they go through the same boot services table as defined in the UEFI specification, but they are now going into Rust functions underneath. Now, ideally, we wouldn't go through a C-based interface to get to the Rust code, but what this is showing is that compatibility is maintained as you swap out the core with all of this code that has previously been invested in. Now that we've looked at some different types of modules, we're going to look at why it is so important that the core has been written in Rust as opposed to just focusing on top-level modules. Here we are showing how firmware flows throughout the ecosystem. The vast majority of firmware code is written at the top level, specifically in this example as the Tiano Core EDK2 level. It then is used by silicon vendors whenever they create new SoCs in order to allow those to boot on reference boards. Those boards are given to other manufacturers down the line. They continue to customize those as needed, targeting a specific product segment or SKU of a product. And ultimately, they land at an OEM that is going to finish fully customizing that firmware for a particular device. As noted here, the majority of that code is at the top level. We're talking large, like somewhere around 75, 80% of that code. So by focusing on the core being written in Rust, we can depend on this natural flow of the code ultimately ending up devices being written in Rust. And that is why it is important that Patina provides this core. And over time, these vendors can pick up that Rust core and continue to supplement it with Rust components and other functionality so that more of the devices that are released will be written with Rust firmware. The Dixie core architecture here may be a little more complex than needed to get started with Patina, but what this is meant to show is a more visual way to view what exactly makes up a Dixie core. And this is common between both a C Dixie core and a Rust Dixie core. It's just the architectural levels of how they are organized. At the top level are the Dixie drivers. These are the hundreds of drivers that were mentioned that participate in initializing the system itself and depending on underlying core details. These drivers at this level you can think of as being both the boot services drivers, the runtime drivers, and the UEFI applications. Those interact with a set of specification defined services, whether it's the UEFI boot services, a special set of services called the Dixie services table, the UEFI runtime services table as well. These are all ways that those drivers can depend on stable interfaces in order to do the work that they need. Now, Patina implements the boot services table and the Dixie services table and portions of the UEFI system table today. Because it does not implement runtime functionality, as I mentioned before, it's a monolithically compiled binary that is a boot services binary. Those come from separate drivers, so you'll see that block without an arrow coming down to the Dixie core path for Patina. Now, Patina implements all of these separate subsystems in pure Rust. So if you're using a crate like UEFI RS, you get a lot of advantages of the Rust programming language while you're writing that code. But underneath, all of these subsystems in the actual firmware are implemented in C code. So Patina implements the dispatcher, image services, the event subsystem, and all of these things with full compatibility to the interfaces that are exposed to the drivers above. Finally, at this bottom layer where we see the architectural Dixie drivers, these are separated out because in a normal Dixie core environment, or like in the Tiano core Dixie core, these are separate drivers that the core depends on, and it uses the protocol interface in order to access these things. In Patina, because we are monolithically compiled, we don't want to have all of these separate EFI binaries providing these services. Ideally, we would pull these services into the core itself. We've started doing that, and the green boxes show which ones have been pulled in. So if you are building a Patina platform today, you do not need runtime Dixie.efi or CPU Dixie.efi. But we still have some of those architectural drivers that are required in blue. The orange ones are runtime drivers, and we don't have a plan to pull those into Patina today, so we will continue to use the PI-based dispatch mechanism to load those drivers. We may rewrite those in Rust, but they will remain separate EFI binaries per the current plan. Taking a look at memory safety and how it's impacted by a C driver versus being able to move things to a pure Rust component is an important aspect of working with Patina because we get a lot of benefits by writing code as Patina components instead of keeping them around as C written Dixie drivers. On the left side, it's showing a Patina component written in pure Rust. This has a lot of advantages of memory safety, including the fact that it allocates from the heap using normal Rust mechanisms. So it's intuitive and easy to use from a Rust perspective, but also participates fully in the Rust memory safety model. Over on the right side, we have a C Dixie driver. It's going to allocate exclusively through C function pointers, and that's what allows compatibility with the Patina Dixie core is those allocation functions are in the boot services table. So regardless of whether they go to a underlying C Dixie core or Patina, they will work. But we're working entirely in C here with raw function pointers, and it's opaque to a lot of the advantages that we have with Rust, like the borrow checker. There's no aliasing or lifetime guarantees, obviously. As we get down to different services and ways to access functionality, Patina does this through the Patina service model. These are pure Rust idiomatic interfaces that are type safe and account for memory safety at compile time. Whenever we go through a binary interface, like a protocol definition, from Rust code, we are having to trust that that interface is correct, but we have no way to confirm that. And that's a key reason why we want to move more and more code to Rust, is that whenever I said earlier we have hundreds of Dixie drivers, those hundreds of Dixie drivers are producing even hundreds of more protocols. And those protocols have functionality that is dependent for code written in Rust. So whenever that code has to call back in, we really want to go through Rust interfaces. We don't want to have lose this memory safety information going down into calls to C functionality. Now we avoided this in the large part by writing the core in Rust. That means that all the boot services, the most common set of functionality called through binary interfaces during boot, is written in Rust. But what this is showing is that there are still a lot of protocols being produced by C code, and we need to move those to Rust so we can get the safety benefits there. Let's begin our Patina GitHub tour. We're going to start with an overview of some of the project details, and then I will share my screen and go over the repositories themselves so you can know where key information is. Looking at key repositories in the Patina project, we'll start at the left side with the Patina repo itself. This is considered foundational, containing the crates that are used in the most other places. This includes the SDK crate, the Dixie core crate, and over time, as more cores are added, they will end up here as well, in addition to the overall documentation for the project. And this is where we publish our MD book from that describes the Patina project. Next is Patina components. This crate or this repository has Patina component crates that are separately maintained. These are consumed as dependencies whenever a platform is building a Patina Dixie core. You can choose individual components from this repository to be able to link into your binary so you have that functionality available. Next is the Patina Dixie core QEMU repository. Because Patina is monolithically compiled, that means that we take the Patina Dixie core library crate from the Patina repo on the far left. We combine that with individual component library crates from the next repo to the left, and we build that into a single .efi image targeting a given platform. Now, if you were building Patina for a different platform that you have, like let's say Raspberry Pi, you would have your own repository that would build a binary crate, which is your EFI binary, using these library crates. And inside your repository for this platform, you would customize which components you choose and how you initialize that code specific to your platform. That would give you an EFI binary that you can drop in to an existing build, and that would serve as your Dixie core plus whatever component functionality you've included with that. Now on the far right side, for open source, we use QEMU, and we support both Q35, which is x64, and SBSA, which is ARC64, in order to demonstrate how to use Patina for those two different architectures. And obviously we build separate binaries for each of those platforms, one for Q35 and one for SBSA. So this provides an example that regardless of which architecture you are using, you can look at how these EFI binaries are built and how they are integrated into a full open source platform in Patina QEMU so you can follow a similar path. The flow at the bottom is kind of just showing a very high level way that these connect together. The SDK is used in a lot of different places, whether it's in different core crates or in components or even in the platform build crate. So you might use this in Patina Dixie Core QEMU to implement Rust code specific to Q35, for example. Then that gets used in all those different places. The core dispatches components, aka drivers, and that ends up being integrated into an EFI binary, in this case for Patina, Dixie Core QEMU. And then we end up taking that EFI binary and integrating it into a platform, in this case QEMU. Patina highly recommends compiling this Rust code in a separate repository and workspace from your normal firmware build that is largely going to consist of C code and a different build system. And the reason for this is that the cargo build system is very opinionated, and so are those other firmware build systems. They work best whenever they're separate, and we just share a binary between the two. We try to make working in Patina as easy as possible, and we do that using some tools and abstractions to keep things limited to as few commands as we can, and also make things consistent across the different repositories. One of those is cargo make. Some of the advantages of cargo make are listed in the table to the right, but what it really gives us is a way to be able to abstract how we're going to invoke these different tasks that are needed in order to build and work with the code. The most important one is called the all task. You'll see that at the top command. All runs a lot of other commands underneath, and it's the best way to get prepared to go to CI in a pull request. If you can pass all locally, there's a good chance that you will pass server CI whenever you create a pull request into a Patina repository. The disadvantage of all is that it takes a while to run because it's running everything. So you may want to run individual tasks as you need to based on what you're trying to check. Some of those are listed below. For example, cargo make build will build the code. If you're in a repository like Patina Dixie Core QEMU that builds an EFI binary, you will build the EFI binary with that command. If you are in a repository like Patina that is a library crate focused repo, you will build the code with that command. Cargo make test provides the ability to run all unit tests and so on. So these are all ways that you can run these commands simply in a repo, and you don't have to worry about what it's calling underneath in order to invoke these tasks the way that we want for the project. Setting up Patina is not particularly difficult. It's very similar to how you would set up other Rust-based projects. This lists some of the high-level steps, but we're not going to spend a lot of time here. If you go to the ILMD book published on the Patina repository, you'll find detailed instructions for setting up the project. One of the last things we're going to look at before jumping into the repos themselves is how we have organized the crates and relationships between those. In this diagram, higher level crates may depend on lower levels. Side-by-side categories are independent, and we generally allow crates within a given category to depend on each other. Beginning at the bottom is the SDK. These are the ones that are most available to other crates to be able to use. Examples here include the Patina crate being the primary crate that's used for the SDK, in addition to some other ones that are broken out from that, specialized in different areas. If you are working with the code in a Dixie driver or a UEFI application, you're almost exclusively going to work within the Patina SDK crate there. We have an idea of internal crates. This is functionality that we've broken out into self-contained units that is used for internal usage. Although these are published to public registries like Crates.io, they're really only intended to be used by other Patina crates in the project. These should not be used by Patina components. Continuing up the left side, the next category is core. This consists of crates that represent the core itself, such as the Patina Dixie core, or crates that are meant to be used only by the core, such as Patina Debugger and Stack Trace, given there as examples. And next to that is components. These are individual sets of functionality. They can depend on the SDK. They should not depend on core or internal crates. If you are interested in contributing to Patina, there are a variety of ways to do that and to get information about the project. In addition to this video series, there are other videos from conferences where we have presented on the Patina project. We have the ILMD book that is published on the website in addition to the documentation generated from the code on docs.rs. You can also join our public Patina meeting calls. These are monthly calls that we have that are available publicly. We welcome any questions there about the project. Those calls are recorded and published to the Open Device Partnership YouTube channel if you want to see what those calls have been in the past. On this slide, I'm going to talk about some quick ways to get oriented in the project if you are interested in contributing. The first is to start by forking the repository and cloning it locally. Follow the setup guide in the README and go to the setup instructions in the MD book. You can look at open unassigned GitHub issues if you are interested in some work to do. We do label issues with good first issue if we think that it's a good issue for someone to start with that's new to the project. We may not always do that though, so feel free to look at all the issues and see if there are any that you are interested in. For dev standards, cargo make all is the main way that we wrap a lot of our requirements into what needs to pass into the local build. So you should always run cargo make all. Unit test coverage must be greater than 80%. You can check your unit test coverage locally using llvmcov. We support that with the cargo make command as well. But you can also create your pull request. And in that pull request, if your coverage is less than 80%, you'll see our CodeCov bot leave a comment giving you your code percentage numbers with a link to your coverage over the lines of source code. You can use that as a reference for what you need to improve code coverage on. Finally, everyone needs to make sure that the firmware code that they contribute can boot on a platform. In Patina, we do that using the virtual QEMU platform since that's publicly available and easy to hook into CI. Whenever you create a pull request in a Patina repository, we have a workflow that will take your changes in the Patina code and it will follow the process that I mentioned earlier that goes from like Patina Dixie Core QEMU to using the Patina code to Patina QEMU using that resulting EFI binary. It will follow that full path and it will take the change that you have implemented in the Rust code in the Patina repository and boot it on QEMU to verify that it works. You will see the results of that boot posted in a comment in your pull request. If you see that Patina boot has failed for some reason, we give information in that comment, such as links to the run that performed it, links to the serial log so that you can see what went wrong. And if it was a build failure, you'll see those included as well. In terms of the overall contribution flow, it's pretty straightforward. Push changes to your fork, create a PR filling out the PR template, and then work with code reviewers and watch the CI results. All right, we are now in the Patina GitHub repository, and I'm going to give a tour of some of the important places you can look to help navigate around if you're new to the project. We'll start by looking at the README. So this is just below the files on the main page for the repository. If you come down here, you'll see that we have some badges where we display critical information about the project, whether CI is passing, what our current code coverage percentage is. In the earlier part of the video, I mentioned that we have a target of greater than 80%. We are currently sitting at 86% here. It'll also give you the latest version of the crates that we have published from the repo and how many commits have passed since we did that release. This helps give an idea of how much work has been done since the last crate you would pick up on Crates.io. We have a link to the Patina community call. You're encouraged to join that call. If you have any questions or feedback on the project, definitely join and you can talk to the different developers and maintainers there. We keep unsafe code percentages as changes are pushed to the project in these badges. Over time, these may fluctuate. They won't necessarily always get lower depending on how we refactor the code, but we are cognizant of our unsafe code footprint and we do try to reduce it over time. Throughout the remainder of the text, you'll find what we consider the most important information for someone first landing on the project, and we keep these links updated. So if you are new, definitely at least look through this once and get an idea of the different resources available and the different policies in place. Also, like usual in the GitHub UI, you can click the code of conduct, read that. we encourage, if you're new, that you should read that. In addition to this contributing file, we also make an effort to keep this up to date, and so this has also essential information for getting started if you're a developer that wants to contribute to the project. The other important place to be aware of is if you look at the top right, there's a link here to our MD book that is published. So I'm going to click that and go to that MD book. And that is here. This is where we put our documentation that we want to formally publish, and it covers a lot of different areas. Instead of breaking down documentation into different books or separate places, we've tried to co-locate it all together in this MD book. Um, Looking at the left side, you'll find the navigation for the different areas. But if you are looking for Patina data in terms of motivation for why memory safety matters in firmware, a great place to start is inside our memory safety strategy and the case studies. This will give some examples of actual CVEs in Rust or in C code that are mitigated by writing code in Rust. If you are a developer and you want to understand how the code is organized, you'll find links here as well for that and some kind of philosophical views on the way that we have organized the code with abstractions and layout and things like that. If you're a developer, though, definitely take time to go through the developer guides available here. This will explain how you should document the code, format the code. We also have some special conventions that we use for things like accessing MMIO in the project and crates that we use to do that safely. So depending on what you're doing, you might want to look at these at a high level and see if any of them apply to your current work. And finally, if you are evaluating Patina as a firmware to use on a platform, look at Patina Dixie Core requirements here, and this will summarize what exactly is required from a platform standpoint that is probably not obvious in order to use Patina. And some of the changes that we made compared to traditional firmware in order to improve the safety and the modernization of that firmware. So whenever and earlier in the video said that we are mostly PI spec compliant, but fully UEFI spec compliant, a lot of those PI spec differences are summarized on this page. And if you have read through this and you have an understanding of what the differences are and you just want a quick summary, we also provide this checklist over here on this page. And this is a way that if you're going through your platform code, you can look at the requirements for Patina and determine if you've updated your platform to comply with those requirements. In addition, we also have a tool called the Patina Readiness Tool, and that is available as well in order to run on a platform. And what it will do is programmatically go through this checklist and determine if your platform meets the requirements or not. We will have a separate video on the Patina Readiness Tool. I'm now going to go back to the repository and show how some of the breakdown I gave of crates applies to what's actually here. So this folder called components right now has a large set of components that we will over time likely move to the Patina components repository. That repository was just created and we haven't moved existing components over there yet. But these are the component crates. Going back up, inside core, we have a lot of those, we do have those core crates that are used by the core environment itself. So these are things like the stack trace and debugger mentioned in that diagram. The Patina Dixie Core crate is a standalone core environment, so that is listed here. And the SDK crates are listed in this SDK folder. As mentioned earlier, the main SDK crate to be aware of is the one called Patina. This is the one that provides a lot of the interfaces that you will use to write code in the Patina components. And even if you're writing some drivers that are not necessarily using the Patina core, this can be used as well. Let's go to Patina Dixie Core QEMU. So all of these crates are maintained here and published from this repository. And whenever we're testing firmware, we need to now, following the Patina model, take these library crates, these generic sets of functionality, and we need to bind them to a platform definition. So that's what we do in the open source code in Patina Dixie Core QEMU. In this repository, we have this bin folder, and we have separate files here for Q35, SBSA, and OVMF. These are the different platforms that we can build binaries for, and they link together those crates from the other places for that platform. So let's go into an example of like the Q35 file. Inside here, we are taking code from the Patina Dixie Core crate and the Patina crate, alongside several others, as you can see. And we are going to combine those together in order to build a monolithic binary that applies specifically to the Q35 platform. All of this is set up in this file in such a way that it's specific to the platform. So some of the details that are platform specific are, if for a virtual platform, for example, how do we exit that platform? We have a crate here called QEMU exit we use in order to perform that action. We also fill in some of the details like what the UART looks like for this platform. It's a UART 16550 IO based using a base port of 0x3F8 and other details, right? So if you think about this, if you're familiar with Tiano Core firmware development, you might see this combining several different concepts. In Tiano Core firmware development, a lot of the code or a lot of the configuration is specified in DSC files. So you'll have DEC defaults and DSCs that will give values for a specific platform, like which IO port to use and those types of details. In Rust, we do that all in code, and this has quite a few benefits. One is we don't have to maintain a lot of custom tooling. Two is by not having a lot of custom tooling, we don't have to have developers understand all these special file formats and maintain a bunch of specifications specific to the file formats. For example, Tiano Core must have a DEC specification, a DSC specification, an INF specification, and so on. Thirdly, we allow this configuration to be checked as part of compilation. So whenever you are actually adding configuration for this platform, we can use compiler-based enforcement to verify that it's being configured properly. And fourthly, this allows us to just have this file be simple Rust. And so you can find everything you need in one place in here. This section here is demonstrating adding some components. I'm not going to spend a lot of time in this video going over the details of exactly how this file is constructed and how components are added and customized, because that will be a focused video by itself. But as you can see, we have a file here for Q35. We have another one here for SBSA. And what these are is it's the way to customize Patina for a platform. So if you are building your own platform, you will create a RS file like this. You will copy and probably paste one of these files as a reference and then customize it for your platform, substituting things like your UART details into this file and what components you want to use and how you want to configure those components. Now we're going to move on to the Patina QEMU repository. So the goal of Patina Dixie Core QEMU here is to build those EFI binaries that combine the Dixie Core alongside the components that we selected. Now that we have that .EFI binary, for example, here for Q35, I'm going to show in Patina QEMU how we bring that in. Over here, we have a script called build and run rust binary.py. This is a Python script that we use for development in order to take that EFI binary that was generated in the other repository, and as it mentions at the top of the file, We patch that into the QEMU platform firmware and run QEMU automatically. Now, this entire process is very fast. Whenever this script is run, it will automatically build your firmware in Patina Dixie Core QEMU. It will take that EFI image, uh, patch it into the QEMU ROM automatically by finding where the existing Dixie core is in that ROM image, and then it will launch QEMU. So you run one command and you get the Rust build, the patch into the ROM, and QEMU execution happening. This script has some help parameters in order to show how to use it. So whenever you are using it, just run the help command in order to see what the options are. These are the options here. But again, we'll have a developer focused video on how do you update those bin.rs files and test them. In that video, it'll go over more detail about how exactly you run this command and do that. But what I want to mention here is that from a developer loop of writing code and testing code, it is very fast and very efficient using this script and the different repositories as they are separated. Now, this repository's its main purpose is to provide the full firmware image for QEMU. So we use that patch script, but ultimately this repository is going to give us a platform like Q35 or SBSA. We can find those in the platforms directory, and here we have the respective folders. If I go into here, we're going to see a Tiano Core PI style setup where we have an FDF file, a DSC, a DEC file. And whenever we take the Patina Dixie core and place it into a platform, we are doing that at the flash file level. It has already been compiled as part of the Rust build over in Patina Dixie Core QEMU. So we don't need to change anything in the DSC other than remove the C Dixie core from it. But in the FDF, what we will do is have the Patina Dixie core come in through here, and we will see that right here in this section. So there's going to be a firmware volume. We place it in its own firmware volume. You don't have to. We just do that because this is a virtual platform and it's convenient to do so. But we have a firmware volume here called Rust Dixie Core, and you can see we assign a GUID to it that is required for the Patina Dixie Core to identify it. And then inside that, we just pull in the EFI binary that we generated over in the Patina Dixie Core QEMU repository. We pull that in this case through a NuGet feed, but you can pull that in however you want to. You can publish it to a binary artifact feed and pull it in to your workspace using some background process, or you can simply just get that EFI file and set up a symlink to it and have this path point to that. For this project, this is just what we do here. And the patch script that I mentioned earlier, it knows how to find the path. In some cases, you might need to specify it, but it can find the path to your EFI binary over in the Patina Dixie Core QEMU repository, and it will patch it over the binary ROM generated from this repository. So that does not build the actual QEMU firmware in this repo. It patches it. If you want to build the firmware in this repo, then we have instructions to do so. But in most cases, whenever you're working purely in Patina Rust code, you're not going to build all of the drivers that are in this repository from source, because that would take a long time. You're going to build the code in Patina Dixie Core QEMU, get that one EFI binary, and then we're going to very precisely replace that in the ROM image over here. And then finally, you'll boot on QEMU, which is the whole purpose of this, and that is your main flow throughout the repositories. That's also the end of this introductory video. Thank you again for sitting through the entire video, and I hope you can watch the others and work with us in Patina.